Okay, so that takes care of part A and B on the homework problem. Let's keep going down. Part C, we say, sorry guys, it keeps spazzing on me. It doesn't want to stay down the first time I pull it down for whatever reason. We're told that the solution part B is then titrated with 0.1 molar HCl. So remember, titration is where we actually have a reaction. And what we're given here is an acid. So, in other words, we have a base to begin with, which is this guy right here, okay? And we have an acid. Those two are what's reacting. So our first step with this is to actually write a reaction. Kind of like what we did in honors chemistry where, hey, you have a reaction and you're trying to do stoichiometry calculations, then you have to write the reaction. So our reaction is going to be C6H5NH2 aniline plus HCl, which I'm just going to write as H, just because the hydroxide, just kind of like the hydroxide on the last one where we just wrote hydroxide instead of sodium hydroxide. We're just going to write the H because HCl will dissociate completely, and it's not the chlorine that's reacting, it's the hydrogen that's going to be reacting. Okay? That's going to form C6H5NH3+. Okay? So that's our reaction. Now, from here, with a titration, remember, it is actually reacting. This is not an equilibrium. It will reestablish equilibrium once the titration is completed, but what we have to do first is figure out who's still in solution after this reaction takes place, okay? And we'll figure that out by basically doing stoich, our best friend. So to do stoichiometry, remember we need moles, so we need to calculate our mole values. Well, how do we do that? Well, we know our molarities and we know our volumes, and we can jump back up here to part B to get the molarity and volume of our other ones. So up here, we have a 0.1 molar solution and a 25 milliliter solution. Well, to find molarity, stop it, sorry guys. Remember, we take our molarity, moles over liters, and multiply it by our liters. So molarity is 0.1, correction, there we go. It's 0.1 times 0.025 liters, and that's going to give us 0.0025 moles, and that's for our aniline. Okay, we'll do the same thing with a hydrochloric acid. Again, we have a 0.1 molar solution, but this time we're only using 5 milliliters, so 0.005 liters. That's going to give us 0.0005 moles. Okay, and that's going to be for our acid up here. Okay, so that gives us our mole calculations. Also, this is kind of like a reset button as well. So we are assuming that the aniline has not established equilibrium, and we have 0 of this, the conjugate acid at this point in time. So from here, we're looking at a stoichiometry problem that's a limiting reactant because we have 2 given values, and the smallest one we assume reacts completely. So we're subtracting that value from both of these and adding it over here. It looks a little bit like an ice table, okay, except these are mole values. And we're also doing to completion, whereas in an ice table we don't, and that's okay. So from here, we end up with these values. Now notice we have the base and we have its conjugate. So in other words, what we're kind of creating here is a little bit of a buffer solution. And what we need is the original reaction. So I'm going to bring this back down. Let's see if it spazzes on us. No, it seems to be behaving. We have the original reaction. The reason we're going back to the original reaction is because we still have some of the original guy left. So that's who we're going to be using. Now, to figure out what the pH is, remember who we're looking for is our either hydroxide or hydrogen ion, in this case hydroxide. Okay? And the hydroxide is going to be being produced from the equilibrium between the aniline and water. And now that we have some of the conjugate acid that was produced from the titration reaction, that means we have some product already in this equilibrium, think like a buffer, okay? Which means it's going to push the reaction a little bit more this way, so we're not going to make as much hydroxide as we did in problem B. Which means problem B, we were told our pH was 8.82. So chances are it's going to be a little bit less basic because there is less hydroxide being formed. So we're expecting a little bit, pH a little bit closer to 7. So let's see what we actually get here. We have to, first off, set up our ice table. And if we remember, what goes in our ice table is molarity. Well, up here we have moles. So how do we get into molarity? We divide by our liters. In this case, we had 5 milliliters that we added to the original 25 milliliters of our original solution. So that means we have right now 30 milliliters, so we're going to divide by 0.030 liters for both of these guys. Okay, and what I'm getting for those is for the base of 0.002 divided by 0.03, I'm getting 0.067 molar. And for the conjugate acid, the 0.0005 divided by 0.03, getting 0.017 molar. And again, we're assuming 0 hydroxide, and we don't care about the water. So minus x, plus x, plus x, 0.067 minus x, 0.017 plus x, and x. And again, we're looking very much like a buffer because that's essentially what we have. Now, how do we solve for x? How do we solve for hydroxide? Well, that requires our K expression and our KB, which remember we calculated KB up here, so 4.37 times 10 to the negative 10th. 4.37 times 10 to the negative 10th is going to equal products over reactants, so 0.017 times x divided by 0.067. And remember, we're getting rid of the minus x and plus x because K is so small. We're assuming that 0.017 plus x and 0.067 minus x are essentially those original numbers. So let's get what that value is. Okay, and what I'm calculating is x is equal to 1. Looks like we've got 2 sig figs now due to our molarity, and I don't know if that was my fault or if that's actually what we're calculating. That's actually what we calculated due to the volume and molarity. So we'll stick with 2 sig figs. So 1.7 times 10 to the negative 9th molar. And if we look, that is our hydroxide ion concentration. So how do we calculate pH from here? We take the negative log of that value. But what are we calculating when we take the negative log of that value? We are calculating pOH, and what I'm getting is 8.76. So this is our pOH value. So we need to get that into pH. How do we do that? We subtract this value from 14. So 14 minus 8.7 is going to give us a pH of 5.24. So the pH for this solution after we add the acid is 5.24. And we're done. So that's our first set of titrations, our first titration problem here. Let's look at part D. Part D, I'm going to move part E down a good bit, or at least a little bit. Okay, so part D is dealing with the continuation of the titration. So we're still adding the hydrochloric acid to the aniline, which means we're using the original reaction right here. Now, do we remember what equivalence point means? Equivalence point is where the moles of the acid equal the moles of the base. Well, the original reaction was up here, so I've moved it. But we started with 0.0025 of the aniline, which means down here we're going to start with that same value, because again, remember we do a reset button to make our math a little bit easier, so 0.025 moles. Well, at the equivalence point, we have that same value of moles of the hydrochloric acid. Okay? And 0 of this guy. Well, look at those two numbers. They're going to react completely because they're the same number, same amount of moles, and it's a 1-to-1 mole ratio. So 0.0025 subtracted from both of these, being added over here, okay, which means we have 0 aniline left, 0 hydrochloric acid left, and 0.0025 moles of the conjugate acid. Okay, so now from here, check out what we have left. Base is gone, acid is gone, we have the conjugate acid left. So we have to ask ourselves, is the conjugate acid going to react in water? Our answer is yes, because it's coming from a weak base. So let's look at that reaction. Let's see if we can write that reaction. Okay, if he's going to react with water, how is he going to react with water? Well, notice the positive. Also notice we're calling it a conjugate acid. So that means the acid's going to give up the hydrogen, forming hydronium and our aniline ion. Well, if we want to find the pH of this guy, we need to figure out the concentration of our hydronium ion. How do we do that? The same way we find the pH for everything we do in this class, just about, which is an ice table. Well, what goes in our ice table again? Molarity. How do we find molarity? Moles over liters. So this is a little bit interesting because we have moles, and here we weren't actually given a volume, but the volume is actually very easy to calculate with MAVA equals NBVB. Remember, this is only true at the equivalence point, and that's because if molarity times volume gives us moles of the acid, and then molarity times volume gives us moles of the base, so at the equivalence point, moles of the acid equal moles of the base. So the acid was a hydrochloric acid. We knew it was 0.0 molar. Okay, we're trying to figure out the volume we added. We started out with molarity of 0.01, and we had 25 milliliters. Well, so if I solve this out, the volume of the acid was also 25 milliliters, which means I have a total of 50 milliliters in this solution. So I'm going to take this mole value and divide it by 0.050 liters. Okay, and that's going to give us a molarity of 0.050 molar. Don't care about water, 0 hydronium, 0 aniline, plus x over here, 0.050 minus x, and x. Now how do we solve this? We need a K expression. Well, here's our problem. What was the K we were using earlier? Well, if you remember correctly, we calculated KB, right? Go all the way up here. What is this guy? He's a KB. That's a problem. What we need for our reaction that we're looking at right now, if we look at it, this is an acid. So what we actually need is a Ka. Well, how do we get Ka? KB, Ka times Kb equals Kw. So our Ka can be calculated by taking our Kb value, which was 4.37 times 10 to the negative 10th, equaling Kw, which is always 1.0 times 10 to the negative 14th, and calculating out what that value is. And that's going to give us a Ka of 2.3 times 10 to the negative 5th. Now we can solve for x. 2.3 times 10 to the negative 5th equals x times x divided by 0.05. Well, we know how to solve this. We multiply by 0.05. X gives us x squared. Take the square root of it. And what we get is x is equal to 1.1 times 10 to the negative 3rd. And that is our concentration of hydronium. Well, how do we find pH? We take the negative log of that value, and that's actually going to give us pH here because we're dealing with hydronium. So negative log of 1.1 times 10 to the negative 3rd, and we get a pH at the equivalence point for this titration to be 2.97. So if you remember when we talked about titrations in class, we said if we had a strong acid, weak base titration, if you go back and look at your notes, the pH for these titrations at the equivalence point is above 7. Okay? Last part of this problem is kind of weird, but it's actually very easy. When we're looking for an indicator, we want the indicator to change colors around the equivalence point, which is, in this case, 2.97. Well, the pKa associated with the indicator is the indicator changes colors at this pKa range, or at that pH range. This is corresponding to the pH range. So in other words, if we look at the aerotyrosine, as how I'm thinking we pronounce that, notice it has a pKa of 3, meaning it changes colors at a pH of 3. This one changes at a pH of 7, pH of 10. Well, our pH at the equivalence point is about 3. We want the one that changes at 3. Okay, so that's it on this problem. If you have any questions, let me know, and hopefully it helped. See ya.